Seriously? Didn't they know there was going to be candy?
They know.
You want to pass the candy? I want some candy.
About the kinds I like. Hopefully you guys like the same kind. Like a lot of chocolate.
Chocolate's good. All right, so thought it might be good to start by looking at this one more time. We got almost to the end of 10.1 last time. Just a couple more examples, and I really think of this as mostly like a vocabulary section. And then 10.2 is some more vocabulary, but there's some actual math in there too. So you have all these different kinds of graphs for modeling different kinds of situations. Simple graphs have undirected edges, no multiple edges, no loops. And so later on, most of the stuff I do is going to be simple graphs. But you also have multigraphs, which do allow multiple edges. You have pseudographs, which allow loops. And then in your directed graphs, simple directed graph, that just means the graphs, the edges are directed. Directed multigraph allows both multiple edges and loops. And then, of course, you have the mixed graphs that have some directed and some undirected edges. Okay, so keep that in mind when we look at this. So this is the first thing we didn't get to. In studies of group behavior, it's observed that certain people can influence the thinking of others. I'm thinking of people at the college. A directed graph called an influence graph can be used to model this behavior. Each person of the group is represented by a vertex, and then there is a directed edge from A to B when the person represented by A can influence the person directed by B. The graph does not contain loops. It's kind of silly to think about people being able to influence themselves, right? And it does not contain multiple edges. Either I can influence you or I can't. There's no point talking about can I influence you 2 or 3 times. Can I or can't I? An example of an influence graph for members of a group is shown over there. And so in this group, Deborah cannot be influenced because there are no edges pointing to Deborah, right? But she can influence Brian, Fred, and Linda. Yvonne and Brian can influence each other. And so the question, it's a real easy question, who can influence Fred and whom can Fred influence? So who can influence Fred? Anybody? Can anybody? Deborah and Yvonne can influence Fred. And who can Fred influence? Just Brian. All right. Good. All right, and then your round-robin tournament graph. A tournament where each team plays every other team exactly once and no ties are allowed is called a round-robin tournament. Such tournaments can be modeled using directed graphs where each team is represented by a vertex. Note that A comma B is an edge if team A beats team B. This graph is a simple directed graph. It has no loops, no multiple directed edges, because no two teams play each other more than once. All right, so here's an example. Team 1 is undefeated. Right, there are no edges pointing to Team 1. Team 3, poor Team 3 is winless. There are no edges pointing away from Team 3. All right, so which other teams did Team 4 beat? Who did Team 4 beat? I think just Team 3, right? And they were beaten by every other team, right? 1, 2, 5, and 6. Okay, but at least they're not Team 3. All right. If I'd realized we were that close to finishing 10.1, maybe I just would have finished it on Tuesday. All right. So actually, before I left on Tuesday, because I figured I'd forget to do it otherwise, I did put up some homework for 10.1. I haven't put up 10.2 or anything later yet. And that's because I decided to put them up, as we cover them. I think that we're actually in pretty decent shape in terms of where we are. I mean, I think at this point really no worse than last semester, so that's good. Maybe, just maybe, we might even get just a little bit into Chapter 11 this semester. That'd be nice. All right. Okay, 10.2, graph terminology. So there's some more vocabulary here, but also a little bit of math. And I actually added some animations to this before I came over, which is nice. Don't like too many words all at once. Okay. All right. First definition. Two vertices U and V in an undirected graph are called adjacent or neighbors, and I think those are both good words for it, if there is an edge between U and V. So if U and V are connected by an edge, one edge, they're called adjacent or they're called neighbors. That edge is called incident with the vertices U and V, and the edge is said to connect U and V. All right. So vertices can be adjacent to each other. An edge can be incident with a vertex. An edge connects vertices. All nice logical terms for those. The set of all neighbors of a vertex, V, is denoted by N of V. N of V, so that's a set called the neighborhood of V. So N of V is just going to be all of those vertices that are adjacent to V. Okay. If A is a subset of V, then N of A is the set of all vertices in G that are adjacent to at least one vertex in A. All right, so try to make this make a little bit more sense for you. All right, so think of this as the set of neighbors of A. Now A is a set of vertices. So the vertices in this big set are going to be anything that's adjacent to any vertex in A. Any vertex in A. All right, if you are adjacent to any vertex in A, you get to be in this set. Okay, that's the neighborhood of A. All right, so the neighborhood of A is the union of the neighborhood of all the neighborhoods of V for all the vertices that belong to A. I kind of wish I had, well, we'll get it. All right, and the last one for right now. The degree of a vertex in an undirected graph is the number of edges that are incident with that vertex. So you just count how many edges are incident with that vertex, and that's the degree of the vertex. And the way we write that is DEG of V, the degree of V. A vertex of degree 0 is called isolated. And I remember you saw an example like that the other day. Actually, let me draw something that's going to have both of these. All right, so there's a graph on 5 vertices. I'll call these A, B, C, and C, D, and E. Vertex C is isolated. You see that? So it has no edges connecting to it. All right, and then a vertex is pendant if and only if it has degree 1. So I have to tell you, I was unfamiliar with this term before I saw your book. Vertex of degree 1 is also called a leaf. All right. So you have one of those in this graph too, right? Vertex B. that make sense? No? It does. Okay.
Definition 2, can you do the second part again?
The second part. Okay, you know what? Let me try to do this.
Picture.
Yeah, I'll draw a picture. So let's try to make it kind of a, let's see, I think 6 vertices should be enough. Okay. So, la-da-dee, da-da-da-da-da, la-da-da, da-da-dee, and one more. Okay. So let's say this is A, B, C, D, E, F. Okay. And let's make set A be just some of those vertices. Let's make it, let's use A, B, and E. Okay. So the neighborhood of A is just all of those vertices that are adjacent to something in set A. All right? So for example, vertex A, which is a member of big A, vertex A is adjacent to F and C. All right? So F and C are going to be members of the neighborhood of set A. Okay? The neighbors of B are just E. And the neighbors of E are B and F, just B and F. Right? Well, that's kind of interesting. Okay. So you get to belong to the neighborhood of A if you have any neighbors in set A. Does that make sense?
Neighborhood of big A.
Neighborhood of big A, yeah. Yes, that's right. If it's an if there's an edge between those two vertices, directly between, direct connection. So I want to point out, like in this example, A and E are not directly connected. There's A and E are not adjacent. Okay, because there is even though there's an edge from A to F and there's an edge from F to E, there is no edge directly from A to E. That's not the same thing. All right.
So E wasn't a member of A, then F wouldn't be a member of A.
No, I think F got to be a member of, F got in because it was a neighbor of A, of little a.
Oh.
All right, so yeah, the first two that I wrote down were F and C because those were the neighbors of little a. Right?
Probably highlighting on the graph with different colored pens.
Oh, there you go.
But is it okay that E is both?
Yeah, in a set, you only list things once, though. Once they're in, they're in. Okay.
So
Oh, yes, you're right. You're right. I missed that. Yeah, because it's a neighbor of E. Okay. Yeah, I like your idea of the color coding. I like color coding. Let me see if, okay. All right. So F and C are the neighbors of little a. E is the only neighbor of little b. And then the neighbors of little e are F and B. So yeah, B needs to be in there. Right?
E can be both of
Yes. Yeah. Make sense?
The neighborhood of a set of nodes is just the set of nodes. Oh my goodness, you would have thought. It would be nice to have it written for definition 2.5.
That's right. You're used to calling them nodes, huh? Right. Hmm? Mm-hmm. Mm-hmm. Yeah, if you call them nodes, I'll know what you're talking about. All right. Okay, so here's another sort of, example like some of the ones we had in 10.1. What does the degree of a vertex represent in the acquaintanceship graph? All right. So you remember the acquaintanceship graph, that was one of the examples from 10.1. So in the acquaintanceship graph, two people are connected by an edge if they know each other. If they know each other. Okay. So I am one of the vertices in the acquaintanceship graph, and so are all of you. So what does your degree represent? Try that again. What does the...
Were you saying words? God? Oh, God. I heard degree.
Yeah. The degree of a vertex. Give me a number, or not, don't give me a number, just tell me what the number means. Right. What does it represent in terms of acquaintances? That's not exactly it.
Can you define an acquaintanceship graph?
The yeah. Okay. So the acquaintanceship graph, the vertices are all the people in the world. And two vertices are connected by an edge if those people know each other. If they know each other. So remember, the degree of a vertex represents how many edges are incident with that vertex. So here's a vertex, and let's say it has that many edges. The degree of this vertex is 4. All right.
And then what was the acquaintanceship graph was?
What was the acquaintanceship graph?
Yeah, the definition.
Two vertices are connected by an edge if those two people know each other. Here, let me pull it up here because I think it's in 10.1. Just have to find it. Here it is. You can use a simple graph to represent whether two people know each other. Now, I remember we talked about this because it came up. You have to assume that if I know you, then you know me, right? To make it undirected. Okay. So if two people know each other, they're connected by an edge. Okay. So now the question is, what does the degree of a vertex represent in that graph? Let's say a particular person has degree 20. What does that mean? 20 what? They know 20 people. That's what it means. Yeah. They know 20 people. Right? And that's not a lot of people, I don't think. If we're talking just about people you know, all right? If we're talking about people you're friends with, that's something different, right? But people you know, well, it says right here, in one study it was estimated that the average degree of a vertex in this graph is 1,000. So what does that mean? The average person knows 1,000 people. Knows 1,000 people. So I don't, you have to, I guess, kind of carefully define what do you mean by know. Do you know somebody if you met them once? Well, that's probably about right then. All right. Oh, now some math. Show that in a simple graph with at least two vertices, there must be two vertices that have the same degree. I think we did a problem kind of like this once before. Okay. So remember, simple means undirected, no multiple edges, no loops. Okay, so at least two vertices. Suppose n is at least 2.
Oh, this is not vector free?
The one I was thinking of wasn't.
Okay.
You might be able to do it that way, though.
So you just you number the nodes by the integers and that's it. And then you just show the base case and the vector stuff. As long as you make a rule.
Right, right. So what I would have to think about is, okay, so let's say you assume that it's true for a graph with k vertices. Show then that it has to be true for a graph with k plus 1 vertices.
Yeah.
Okay. Yeah, there might be a way to do it that way. I was thinking of something else. Here's what I was thinking. Each vertex has degree 0, 1, blah, 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 up to n minus 1. Okay? It has to be one of those things. It has to be at least 0 if it's an isolated vertex. And at most, it's n minus 1 because the most connected you can be if you're a vertex is that you're connected to every other vertex in the graph. Does that make sense? Okay. Okay, now at first it looks like that's not going to do me a whole lot of good because how many numbers are in this list? No, no, no. How many? Well, from 1 to n minus 1, there's n minus 1, but I included 0, so there has to be how many? N? Okay. Now, if you have n vertices and those vertices have n different degrees, well, this is saying that can't happen. So I have to argue that can't happen. So suppose there is a vertex of degree 0. If there is a vertex of degree 0, that means it's isolated. That means there can't be a vertex of degree n minus 1. Isn't that right? I remember we did a problem just like this once. I don't remember how they dressed it up, all right, but it was the exact same idea. All right. You see why that's true? If there's a vertex of degree 0, then you can't have a vertex of degree n minus 1 because n minus 1 means that that vertex is connected to every other vertex. All right, and it can't be connected to every other vertex because there's one vertex that's not connected to anybody. Okay? And vice versa. I'll say and conversely. If there is a vertex of degree n minus 1, that means that vertex is connected to everybody. There can't be any vertices of degree 0. All right? And that just reminds me a little bit of grammar. Yeah, there's one vertex and then there's multiple vertices. Kind of a weird English language holdover from Greek. Same thing with if you take Math 8, linear algebra, you have one matrix, you have many matrices. So yeah, it's the pigeonhole principle. You can have degrees 1 through n minus 2, and you can have a 0 or a n minus 1, but you can't have both. All right? So that means that there are at most n minus 1 different degrees. Right? And since you have n vertices, that's pigeonhole principle. And I suddenly forgot how to spell pigeon. P-I-G with no D. Make sense? Questions? I wish I could remember. I think it was in the pigeonhole principle section we did a problem like that, but again, I can't remember how they dressed it up. Definitely wasn't about graphs. Had to have been about something else. All right. Oh, this is fun, the handshaking theorem. So you see why this is called the handshaking theorem, even though it's a theorem about graphs. Right? When you add all the degrees of all the vertices of a graph. All right? So the sum of degree of V for all vertices in V, big V. Okay? Each of the edges in the graph is going to contribute 2 to that sum. All right, let's say that I get to this edge. I'm going to go around and look at all the different edges. A is going to get counted, B is going to get counted. All right? So each edge contributes 2 to the sum of the degrees of the vertices because each edge is incident with exactly 2 vertices. All right? Here, let's, I wish I still had that picture up from earlier. I'll do a smaller one this time. I'll make it degree 4. And let's say it's like this and this and this and like that. Okay. All right. So first I'm going to look at vertex A. Vertex A is incident with this edge and this edge. Then I'm going to look at B. B is incident with this edge. I'm going to look at C. C is also incident with that edge, and it's incident with this and this. D is incident with this one and this one. So each edge got counted twice. And so if you want to know what is the sum of the degrees, it's exactly 2 times the number of edges. 2 times the number of edges.
So the degree is basically just G is going to be C and C can be
Right. The degree is how many vertices is that thing adjacent to? Or how many edges are coming out of it? Put it that way.
And that's why it's counted twice, because it has B, C, and D.
Correct. Yep. All right. So that's called the handshaking theorem. I got my notation a little mixed up. Let G be an undirected graph with M edges. then 2m is equal to the sum of the degrees of all the vertices. You add up the degrees of all the vertices, it comes out to 2 times the number of edges. Okay. All right. Find the sum of the degrees of each of the vertices in example 1. Verify that it equals twice the number of edges. Where is example 1? Ah. Okay. All right, so I'm going to go in order from A through G, and I want you to tell me what is the degree of each vertex. All right, starting with A, the degree is 2. B, the degree is, what is it? 4. This one is 4. This one is, did you say 4? It's 1. Okay. All right. These are in a funny order. E has degree 3, F has degree 4, and G has degree 0. So 3, 4, 0. And those add up to 6, 10, 11, 14, 18. Okay, so now you count the number of edges. Edges can be a little tricky to count. It's easy to lose your place. I usually try to go from left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9. You see the 9? Yeah, so that works. That's all they wanted us to do, just verify the handshaking theorem. No, there aren't 18 vertices. The degrees of the vertices add up to 18. Show that the, oh, okay, so this is why it's called the handshaking theorem. I was waiting for somebody to ask me. Show that the sum over the set of people at a party of the number of people a person has shaken hands with is even. Assume that no one shakes his or her own hand. Okay, well, I hope not. All right. Okay. All right, so let's say that your vertices are the people at the party. And then U and V are connected by an edge if those people have shaken hands. Okay. So for each vertex, for each little v in big V, the degree of V is the number of people V has shaken hands with Okay. So if you add up all those numbers, we know from this handshaking theorem that's 2 times the number of edges. I guess the number of edges, let's say that no two people shake hands more than once. All right? Maybe the first time they see each other at the party, they shake hands. Okay? Then if that's true, if no two people shake hands more than once, then M is the, well actually 2M is the number of handshakes. Is that right? No, M is the number of handshakes. Anyway, by the handshaking theorem, that sum, the sum of all the degrees, is equal to 2M. And of course 2M is even. Yeah, M is the number of handshakes. That's it. Pretty simple. All right. Oh, this is fun. All right, I'll just walk you through this because it's all up here. This theorem's kind of a big deal. An undirected graph has an even number of vertices of odd degree. Does that make sense? It sounds a little weird when you first read it. An even number of vertices of odd degree. All right. So draw some graph, make it as crazy as you want. Not too crazy. You don't want to give yourself a headache. I'll give myself 8 vertices, and I'll do something like this, and then I'll go like this, and then I'll go like this, and like this, and like this, and maybe like that. Okay. So far, so good? All right. So the theorem says that there's going to be an even number of vertices of odd degrees. So let's look at all the degrees. This one is 2. This one is 3. This one's 2. This one's 2. I have a lot of 2s. This one's 1. That's 2. This one is 1, 2, 3, 4. So in this case, there are 2 vertices of odd degree. And 2 is an even number. Okay. Let me see if I can wreck that by adding more edges. Let's mess up the odd ones. Well, that odd one and this odd one maybe. And let's see. Maybe I'll throw in one here. And I'll throw in one. I don't want to do it there. Let's do it here. Okay. So I think a bunch of the degrees change. This one now is 3. This one is 1, 2, 3, 4. This one is 1, 2, 3, 4. 1, 2, 3. That one's still 2. This one is 2. 1, 2, 3, 4. That one is 4. That one is still 4. Okay, and I still have 2 odd vertices. I was hoping I would at least end up with some number other than 2, like maybe 4. All right? But anyway, it's still even. Okay, so this comes from a very cool application of the handshaking theorem. So let me show you what that looks like. Let V1 and V2 be the set of vertices of even degree and the set of vertices of odd degree. It would have made more sense to do that the other way around. Make V1 the odd ones and V2 the even ones. All right, but nobody asked me, so. Okay. So in other words, you're separating your set of your vertices. You're putting the odd degree ones here and the even degree ones over here. Okay. All right, so using the handshaking theorem, 2 times the number of edges is equal to the sum of all the degrees. Okay? And since we have sort of partitioned the set of vertices into V1 and V2, you can separate this sum into the sum of the even degrees plus the sum of the odd degrees. Okay. So here comes the cool part. I can talk you through this part. This number is obviously even. And this isn't too hard to see. This number has to be even. Do you know why? Think about what V1 is. V1 is the set of all vertices with even degree, right? Okay, so I heard one person say it. Why does this have to be an even number? What kinds of numbers are you adding up? You're adding up even numbers, and whenever you add up a bunch of even numbers, you're going to get an even number. Doesn't matter how many of them there are. See where this is going?
Oh, so if you take all the odd numbers and multiply it by 2, it turns them even. And the other said you were even.
Well, I don't know that I see any odd numbers up there yet. We haven't talked about these yet. These are the vertices of odd degree, right? But I can tell you that obviously 2m is an even number, right? That's sort of the definition of an even number. And this sum has to be even because we're adding up a bunch of even numbers. Okay? The number that we don't know about, that the theorem is about, is this number here. And so what we've just found is that an even number is equal to an even number plus that mystery number. All right? So when you add an even number and a mystery number and get an even number, what kind of number does the mystery number have to be? It has to be even. If it was odd, this number would be odd, right? Okay? And that's exactly what we're trying to prove, because these are the vertices of odd degree. Well, let's not. Wait a minute. Because the degree of v is even for v in v1, the first term in the right-hand side of the last equality is even. Okay. Furthermore, the sum of the two terms on the right-hand side is even, because it comes out to this. Therefore, the second term in the sum is also even. Oh, okay. Sorry, I missed one part. Okay. So we know that that has to be even. Now that is the sum of a bunch of odd numbers. Okay. So when you have an odd number plus an odd number plus an odd number, I don't know how many odd numbers there are, it comes out to be even. What can you say about how many numbers are there? Could there be 5? Yeah. If you add up a bunch of odd numbers and get an even answer, there must be an even number of those. And there it is. Okay. So remember, these odd numbers represent the degrees of the odd vertices. And so there must be an even number of those. I think that's kind of cool. All right. Let's see what else we got. Oh, good. This is a perfect place to take a break. So coming up next, and I talked about an example of one of these last time, special graphs, special kinds of graphs, like the cube graph that I showed you last time. So I'm going to show you all those. And last year, I had a it was supposed to be a gimme, exam question where I just asked I asked people to draw some of these. I just wanted to see, do you know the notation? Do you know what W5 means? Do you know what K6 means? Do you know what Q2 means? All right, you don't know right now, but you will. All right, and then hopefully you'll be prepared if I ask you that on the exam. Okay? All right. So special graphs, complete graphs. So complete graph is just a graph with every possible edge, is how I think of it. All right? You find any two vertices, they're connected by an edge. Connected by an edge, connected by an edge. All possible edges. Okay? So they don't start to get interesting until I would say about 4. All right? And so the notation for complete graph is K sub n. So if on the next exam I ask you to draw a K5, that looks like that. And this is kind of funny, I think. A graph that's not complete is called non-complete instead of incomplete for some reason. All right. Cycles. So you can see why they're called cycles, right? So just go all the way around. Okay, consists of n vertices and edges v1, v2, v2, v3, all the way up to vn minus 1, vn, and then vn, v1. All right. So you see some examples of cycles there. And then you have wheels. Wheels are kind of like cycles, except you add, I guess you could call this a spoke in the middle, right? And then you connect the spoke to all the other outer vertices. Okay. All right, and then here's the one I mentioned the other day, cubes. Oh, notice notation. All right, cycles are C, wheels are W, and then cubes are Q. All right. An n-dimensional hypercube, or n-cube, Q sub n, is a graph that has vertices representing the 2 to the n bit strings of length n. All right, so Q2 has 4 vertices, Q3 has 8 vertices. And you can represent those vertices by bit strings. And 2 vertices are connected by an edge if they differ in exactly 1 bit. All right, so like 0, 0, 0 is connected to 1, 0, 0. 0, 0, 0 is also connected to 0, 0, 1. So there's only 1 bit that's different. Yeah? Ah! They're kind of hard to draw. Yeah, because what you're talking about is a representation of a 4-dimensional cube. Huh? Something like that. All right. Yeah, you can see why they only wanted to draw up to 3. All right. Okay, bipartite graphs. These are more special graphs. So let me try to explain this in my own words. A bipartite graph is where you take your set of vertices and separate them into 2 separate sets. All right? And the graph is bipartite if your only connections go from these vertices to these vertices. In other words, you don't have any edges within this set, and you don't have any edges within this set. Well, no, so here are some pictures, right? Notation K23, so that's those are called complete bipartite graphs. So these are the largest possible bipartite graphs from between 2 vertices and 3 vertices. All right. So no connection between these 2, no connections among these 3, only connections between the set of 2 and the set of 3. Okay. There's a K33. No connections here, no connections here, only connections between here and here. Okay. And a graph can be bipartite without being a complete bipartite graph. I mean, la-da-dee, da-da-da. That graph is bipartite. Oh, sure. Yeah. I guess that would count as a K11. Okay. Yeah, no connections here, no connections here. Only connections between the 2 sets. Okay, now what's interesting is it's not always easy to tell by looking at a graph whether or not it's bipartite. Remember we talked the other day, I said the only thing that's important in a graph is which pairs of vertices are connected. All right? So 2 people can draw the same graph 2 completely different ways, but it's still the same graph. All right? So here's a couple of examples. They want to know, are these graphs bipartite? So what you have to do to show that a graph is bipartite is to try to draw it. Well, try to draw the graph in a different way so that it's more clear. Okay. So here's how I do that. Okay, so like this one here. I say, okay, if that graph is bipartite, then there has to be a way to separate the vertices into 2 sets. Call them V1 and V2. I'm going to call this part A. Okay. So that there are no connections within this set and there are no connections within this set. So for example, if I start, let's say I start with vertex A and I put it here. If vertex A is in that set, then all of its neighbors have to be in the other set. B and D and E have to be over here. Okay. Any neighbor of B, D, or E has to go in the first set. So like, for example, there's an edge between B and C. So C has to go back over here. And, okay, that's all of them, right? So now we just make sure that there are, oh, okay, so you know what I can do is I could try to redraw the graph just right here. And make sure that I don't, okay, so A is adjacent to B, D, and E, right? That was the whole point. C is adjacent to B, D, and E. Okay, is that all of them? 1, 2, 3. 1, 2, 3, 4, 5, 6. Yeah, that's all of them. That and that are the same graph. I'm trying to see, is there a clever way to Oh yeah, you know what you could do? I always think of actually trying to pick up vertices and move them. Think of the edges as being like rubber bands. If you just picked up this B and put it over here so that this edge moves there and this edge moves here, now it's a lot more clear, I think. Okay? It's the same graph. That is bipartite. I have a feeling the other one isn't. But I'm not 100% sure. I haven't done this problem in a year. Well, I should give you a minute to think about it. Try to decide whether or not this graph is bipartite. Sometimes it's easier to show a graph's not bipartite than it is to show that it is. Especially if it's a big graph. One way to show that a graph is not bipartite, I don't think that's going to work in this problem because I don't see any, is to show that it doesn't have any triangles in it. And by triangle, I mean a triangle with vertices at the 3 corners. All right. Well, yeah, I don't see any either. But that's, if you can find a triangle, that means it's definitely not bipartite. But if you can't find one, I don't think that necessarily means that it is. Yeah, I like that. I need a way to model that, like on a cork board or something. Yeah. It's just a matter of sitting down and doing it. Yeah. All right, so let's say you put A there. A is adjacent to F and C, right? I'll say C and F. C is adjacent to B and E. So B and E have to go over here. F is adjacent to a whole bunch of things. E, B, oh no, that's okay. F is adjacent to E, B, D. D has to go here, right? All right, so does that all look okay? Let's see. A is adjacent to C and F. B is adjacent to C and F. E is adjacent to C and F. D is adjacent to C and F. C and F are not adjacent to each other. And A, B, D, and E are those outer corners, so they're not adjacent to each other, right? Yeah, so that one's also bipartite. What's that? Oh. Oh, yeah, like this. Right. All right. Good. Subgraphs. Okay, so I was thinking about something with subgraphs a minute ago when I said if you can find any triangles in the graph. So when I said if you can find a triangle in the graph, that's what I was thinking of with subgraphs. So a subgraph is just a smaller graph within that graph. All right, so it contains some of the vertices and some of the edges. Okay. So a subgraph of a graph with vertex set V and edge set E has vertex and edge set W and F. W is a subset of V, F is a subset of E. All right. And just like sets and subsets, you talk about subgraphs and proper subgraphs. All right. So here's a K4. Subgraph could be something like, let's say just these three vertices and just this one edge, I guess. Okay. All right. Oh, and that's it. Okay. That's it for 10.2. Was that 10.2?
Yeah.
Yeah, that's 10.2.
Didn't you find triangle really easy place making these vectors and do vector addition?
I see what you're saying. Yeah, because when you add vectors, yeah, depending on how you draw it, right? So when I think of vector addition, I think of something like this. Yeah. But if you have this and this, then yeah, the sum is that, right? So you just if you're working with a simple graph, you don't take direction into account, right?
You could assign direction real quick.
You could if you wanted to, yeah, if that helps.
I mean, there's a lot of computation libraries to do that really fast.
Oh, okay. Shh. All right. Okay, let me just peek at something here real quick. Maybe we could do some of this. Well, maybe we could get isomorphism out of the way at least. All right. So I remember when I put this together last year. Okay, it has today's date on it. I was thinking we were caught up to last year. Okay. I did a lot of skipping around in 10.3, 10.4. So that's how all this stuff ended up in one PowerPoint. All right. So when I put up the homework assignment for these two sections, it'll reflect that. It's only going to have just these two things. Let's do, I think if we just do isomorphism, that's probably plenty for today. And then we can get into connectivity next time. All right, so isomorphism is kind of along the same lines as are these two graphs the same? All right. Basically, you don't pay any attention to, do the vertices have different names? All right, that doesn't matter. All right, so here's the definition of isomorphic graphs. Simple graphs, G1 and G2 are isomorphic if there is a one-to-one correspondence. You know what I mean by one-to-one correspondence? You list all the vertices. Well, let's make it real general. You list all the elements of one set here, all the elements of the other set here, and a one-to-one correspondence is like a back and forth. All right? It's basically identifying in this graph, let's say you have vertex V1. Maybe in the second graph, the vertex W5 is playing the role of V1. All right, they're basically doing the same thing. Okay, I'll show you. Got lots of examples here. Simple graphs are isomorphic if there is a one-to-one correspondence between V1 and V2 with the property that A and B are adjacent in G1. If and only if f of A and f of B are adjacent in G2. Okay? So when I take two vertices in my first set, say V1 and V2, if those vertices are adjacent, then their counterparts in the other graph should also be adjacent. And if these two vertices are not adjacent, then the counterparts shouldn't be adjacent either. Okay? And that function that goes back and forth between the two vertex sets, that's called an isomorphism. If they're not isomorphic, you say non-isomorphic. All right. So here's a really simple example. Really, really simple. Refresh my memory what you mean by that. Where, like, putting things into in like an efficient way. I'm not sure off the top of my head.
So it would be like determine one, but that necessarily determines the effect, like how you can establish the vacancy of the rest of them.
Yeah, maybe. I'm just not sure. Be something interesting to research. Okay, this one is really, really simple because, again, it comes down to pulling the pins out of the cork board and just putting them down in a different way. Think of this as like a long chain. This is also a chain if you imagine picking it up at this end and just laying it down underneath here, right? That's where my lack of computer skills holds me back. All right. You can lay down that second graph like this. Here's V1. This is going to be V2. This is going to be V4. This is going to be V5. This is going to be V3. It's the same graph, except for the names. Right? So just put this guy down over here. Put this person down over here. Okay. So when you show me your isomorphism, well, the way I'll normally do it in the more complicated examples is I'll actually list the first set of vertices, list the second set of vertices, and you might as well list them in an order that'll, make it easy to see. So the isomorphism would just be like this. Who's playing the role of who? And what you can sometimes do for the more complicated examples while you're trying to figure them out is over here just show which vertices are adjacent to each other. So in this one it's really simple. It goes like this, like this, like this, like this. And then the corresponding vertices are adjacent in this list. V1's adjacent to V2, V2 to V4, V4 to V5, V5 to V3. All right. So those are isomorphic. It almost means they're the same graph, just drawn in a different way. And the vertices have different names.
Okay, so like an example problem would be sort of painting a graph like you did with that.
Uh-huh.
Okay.
Yep. Is there a way to pick it up and put it back down where, the pins are still connected by the same pieces of yarn? It's just that the pins aren't maybe placed the same way.
So when we make an isomorphic graph, do you have to use straight lines or more like curvy lines?
You can make curvy lines. Sometimes, yeah, you can make curvy lines. Curvy lines are still lines. Okay. Yep, doesn't matter if they're straight. Okay, now it starts to get a little more interesting, although, well, yeah, that is a little more interesting. So I remember the first time I looked at this one, I was thinking, well, if you pick up this pin right here and put it down over here, it kind of sort of almost looks like the same thing. Determine whether the given pair of graphs is isomorphic. You have the thing on your... Exhibit an isomorphism or provide a rigorous argument that none exists.
Okay.
Yeah, yeah. Yep, same instructions. Okay.
Oh, yeah.
But, well, except be careful, though, because that's not... First of all, I want to make sure everybody understands, because this takes a little getting used to. Even though this thing here looks kind of distorted, that is exactly the same thing as this from a graph perspective. It's exactly the same thing. The problem is that if I'm thinking about making this play the role of this, there is kind of a difference. Yeah, it's like in this representation, these two vertices are like this, kind of along the same side of the K4. This is a K4. But over here, they're not. So the question is, does that matter? And actually, I think it turns out, the more I think about this, I think it ends up that it doesn't matter. And these do end up being isomorphic, I think. All right.
It doesn't matter how it connects.
Just how it connects. That's the only thing that matters. Now, you can check for a couple of quick things. There are certain things that will rule out, that will tell you that the graphs are not isomorphic. First of one example is you could do a quick check of all the degrees. All the degrees have to be this. You have to have the same degrees in the same frequency. For example, like over here, this is degree 3. This is degree 4. This is degree 2, 4, 3. And so the other graph, if it has a chance of being isomorphic, also has to have a 2, 2 3s, and 2 4s. All right? And I think it does. That's a 3. This is a 2. This is a 4. This is a 3. And this is a 4. Okay? So it passes that test. That is a necessary condition for them to be isomorphic. It is not a sufficient condition. All right. Okay. So let's try this. I'm going to list U1, U2, U3, U4, U5. Okay. And the first thing I'm going to say is that since I have one vertex of degree 2, that vertex has to get mapped to the one that has degree 2 in the other graph. So U3 and V2 have to go together. They have to go together. Your 2 degree 3s have to go with your 2 degree 3s over there. So U1 and U5 have to go with V1 and V4. All right. Okay. So let's see if we can do this. Start with U3. So U3 is adjacent to U2 and U4. V2 is adjacent to V3 and V5. Now, what I have to think about is, should I map U2 to V5 and U4 to V3, or should I do it the other way around? Should I put U2 with V3, U4 with V5? Okay. Well, let's see. Kind of helpful to mark the degrees. So this is a 3, this is a 2, this is a 3, that's a 4, that's a 4. V3 is a 4, and V5 is a 4, isn't it? Yeah. Okay. So this has to go either to this or to this. And then this has to go to the other one. Okay, well, let's see what else we can do. I think... La-da-da-da-dee. Well, let's try this. Let's try making this go here. Okay, check that all of your edges are where they're supposed to be. So U3 is connected to U2 and U4. V2 is connected to V3 and V5. Okay, so now U2 is going to be connected to all of these other vertices. U1, all of them, right? U4 and U5. Okay. So I think the idea is you can kind of do what we did here. Just think of this vertex as being here. And then if you think about it, here, let me redraw this real quick. Okay, so we're going to do that like that. This is going to be V1, V3, V4, and V5. And then I'm going to put V2 over here. And they connect like this. Okay. Basically turns into the exact same graph that you're looking at over here if you sort of think about switching V5 and V4. Imagine picking up the pins and just switching those. Since all of these vertices up here are connected to each other, it's kind of hard to picture if you're picturing it in terms of yarn and stuff, because then things will start to get crossed. But it's actually going to look exactly the same if you switch V4 and V5. All right. So I think what you want to do is we can make U1 go to V1. And then we can make U2 to go to V3. And then make U4 go to V4. I have it going to V5. Wait a minute. V3. Oh, no, yeah, you want it to go to V5, because remember, we're switching these two. Okay. Make U4 go to V5. Make U5, I'm running out of shapes, go to V4. And I don't think I really need a shape for that last one. That last one's pretty clear. Just do a thing like this. Okay. So I think this will work. What I like to do at the very end before I carve it in stone is just check that all of the things that are supposed to be adjacent are adjacent. Okay. So let me get rid of this. All right, and let's check this. In the first graph, U1 is adjacent to U2, U5, and U4. U2, U4, U5. And so I should have those same adjacencies in this one. V1 is adjacent to V3, check. V1 is adjacent to V5, check. V1 is adjacent to V4. Okay, so that looks all right. Then I get to U2. U2 is also adjacent to everything else. I've already checked U1. U2 is adjacent to U3. And V3 is adjacent to V2, right? So those are okay. U2 is also adjacent to U4 and U5. U2 to U4 means V3 has to be adjacent to V5, and it is. And then U2 is adjacent to U5, and that means that V3 has to be adjacent to V4. And that works. All right, U3 is adjacent to U2. We've already taken care of that. I need another color. U3 is adjacent to U4, and V2 is adjacent to V5. Right? Yeah. Okay, U4. We've already got U4 going to U1, U2, and U3. We just need to check U5. I need another color. And then after this, we'll be done. U4 goes to U5. V5 goes to V4. So that works. That works. They're isomorphic. Okay. As you can see, it can be kind of a pain. All right. And when the graphs get really, really big, it takes a long time. Then you want to try to have a computer help you or something. And I think there are algorithms for checking these, or for actually finding the isomorphism. Okay. Lots and lots of things to check. Okay, let me just peek at this last one real quick. I need to decide if I want to, I might want to save the last one. Well, let's look at it real quick, and if we get it right now, we get it, and if not, we'll save it. Okay. Oh. I think I might kind of sort of remember how this works. So I think if you do the degree test, check all the degrees. I don't think that catches it. Usually you don't get that lucky. That's a 3, that's a 3, this is a 2, that is a 2, that's a 3, and this is a 3. So I think you're going to have the same thing in the other one. 2, 3, 3, 2, 2. Guys, shh. 4. Oh, it does, doesn't it? Wow. And that is right, isn't it? I didn't miss a 4 over here? Okay. Well, there it is. Those can't be isomorphic because the second graph has a vertex of degree 4. The degree of V6 is 4. But the degree of none of the U's is 4. Okay, that was a lot easier than I remembered. Right. Okay, that's 10.3. That's the only thing I'm going to do in 10.3. All right. So we got through 10.2, got through 10.3. We'll leave it there.